Kia ora Year 11 and any Year 12s who are redoing AS, and Ben, Tosef and Snehal. This is the second part of the level of the AS stats exam from last week. So this is the March 2020 paper 1-2. That's not the right number. It's actually paper 5-2. And we've got 3 questions here. So the first one is on arrangements, perms and cons. That's question 4. The second one is a distributions question. And the third one is a probability tree question. So I'm going to go reasonably quickly. The question that you're likely to find the hardest in here is this first one, which is permutations and combinations. I can't emphasize enough how many of these questions you've got to do to get good at them. They really can be quite tricky, and the only way I've found to be kind of fluent in what technique to pick is just to do tons and tons of different examples. So make sure you've done the textbook work on this and just watch tons of the videos I've done on perms and comms questions. Okay, so Richard's got 3 candles that are blue, 2 red and 6 green, and they're the same apart from their colours, and he arranges them in a line. So the first thing we've got to do is figure out the number of different arrangements of the 11 candles if there's a red one at both ends. So the way that I do these questions is kind of silly, but it sort of works. I just draw out these little lines, right? And I'm going to draw 11 lines out for the candles, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and we're going to whack an R in at each end. Right, so we've got 3 blue, and we've got 2 red, which thankfully we've used up, and we've got 6 green. Now, there's no difference in the candles, so that means that these two are indistinguishable. So what we've got to do is to figure out how many ways are there to arrange the blue and the green stuff, right? So first we can think about, if the order matters, how many ways are there to arrange it? And that's going to be 9 factorial, right? Because there are 9 ways to choose the first candle out of the 9 here. And that means there's 8 ways left to choose the next one, and so on. And then we get down to the last candle here. But what we've got here is candles that are identical. So the 3 blue candles are all the same. And that means that R1, R2, and R3 is the same as R1, R3, and R2. And so on. So I'm going to take that 9 factorial and I'm going to divide out my double ups. That means I'm going to divide out by 3 factorial. But the same thing is true for the 6 green candles, only this time it's going to be 6 factorial, right? Because green 1, green 2, green 3, green, you get the idea, hopefully. That is the same as like green 4, green 1, green 3, and so on. So that's all there is to this question, right? Because the red ones are sitting at each end. And I don't have to think about swapping those over because they too are indistinguishable. So this question comes down to that set of factorials. There's a whole lot of cancelling out that we can do here. So we've got 9 times 8 times 7. That washes away with the 9 factorial, that 6 factorial does. And now I've got 3 times 2 here. So I'm going to do a little bit of factorising. Here I get 3 here and I get 4 here. That leaves me with 12 sevens are 84. So that's a really nice example of an arrangements question. It's a tiny bit harder than some of the lead-in questions that we sometimes see in the AS stats paper. The next question is one where the mark schedule's got 2 ways to do this, but I think there's one way that is pretty easy once you've seen it. So I haven't done the second way because I looked at it and went, oh, I don't know if I'd ever do it that way. So you're welcome to go and have a look if you want to. This time, we've got to figure out how many different arrangements of the 11 candles if all the blue ones are together and the red candles are not together. So it's always easier to work out when things are together than when they're not together. So what I'm going to do with this problem is I'm going to work out 11 candles, how many ways, and then I'm going to do when the red ones are all together. So this first way is blue together and then don't care about the rest. So red and green can be anywhere. So we're going to do that one first. And then we're going to work out not what they're asking for directly. We're going to do blue together and we're going to do red together. Because what we want is all of these ways take away this number. So just going over what we've got again, we've got 3, let's see, 3 blue, 2 red, and 6 green. If we're doing the blue ones together, we can think about that as a block of blue, 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 and that leaves me with 8 more. So this is very similar to what we had before. Not quite, but just about. We've got 9 things that we're arranging, so that's going to be 9 factorial, right? And then we've got to divide out the double ups, or the things that are equivalent. So for the 2 red ones, we're going to divide out R1, R2, and R2, R1 are the same thing. And for the 6 green ones, we're going to divide out the ones that are effectively the same in there. So we divide by 6 factorial. And when we do that, we get 9 times 8 times 7 divided by 2 because of how this is working. Right? And that gives me, simplifying that out, I get 36 times 7. 36 times 7 is 252. So that's the first part done, right? So that's with the blue together and any different mix of reds and greens. Now we're going to do the blue together and the red together. So we're going to have blue, 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 and we're going to have red, red, and then we've got the 6 greens left to place. 3, 4, 5, 6. So the blue, blue, blue could go here, here, any one of these places. The reds could go any one of those places. So this one is going to be the same as just thinking about placing 8 objects. So it's 8 factorial, and now I've got to undo the fact that the green ones, green 1, green 2, green 3, green 4, and so on is the same as green 2, green 5, green 6. So I'm undoing this one by dividing out 6 factorial. That just leaves me with 8 times 7, which is 56. So what we've got is we've got 252 possible ways to organise when all the blues are together, and we've got 56 of those ways are when the reds are also together. So my answer will be 252 take away 56, which is 196. I definitely think that's the hardest part of this whole paper. So if you got that on your own, I think you're doing quite well. Right, let's have a look at question 5, much easier. So here we've got 70% of adults in Greenton owning a car, and we've got a random sample of 8 adults from Greenton is chosen. At this point, you should be thinking binomial distribution, right? I've got a fixed number of things, 8 adults, and I've got a probability of success, which is 70%. So we have to figure out the probability that the number of adults in the sample who own a car is less than 6. So X is the number owning a car, N is 8, and P is 0.7. We want the probability that fewer than 6 adults in the sample own a car, which is the probability that 5 or fewer own a car. We are going to work that out by saying that we'll work at the other end. Instead of going 0, 1, 2, 3, 4, or 5, because that's too painful, we're going to do 1 minus the probability that 6, 7, or 8 own a car. And you need to show you're working for this. So we'll start with the probability that 8 out of 8 own a car. That's going to be one way for that to happen. Think about your tree diagram, right, which is what the binomial distribution is all about. It's just a massive tree with identical pairs of branches at each level. So we've got 1 times 0.7 to the power of 8, and then we've got 8 ways times 0.7 to the power of 7 times 0.3, and then we've got 8 choose 2 ways for this one here. Now, if I were doing this on a lower than 8 number, I probably would be racing through Pascal's triangle to find those combinations like that. But here, 8 choose 2, well, actually it's not 8 choose 2, it is 8 choose 2, but it's 8 choose 6, right? So 8 choose 6 and 8 choose 2 are the same thing because they are 8 factorial over 6 factorial, 2 factorial. And when you work that out, you get 8 times 7 divided by 2, but it's fine to do that on your calculator. In the AS and the A-level papers, you've got to show you're working for these questions or you will chuck marks away. But in here, that all works out to be 1 minus 0.5517. That gives me 0.448 when I'm rounding to 3 sig figs. Okay, so that's the first part done. Right, the next part is one where we've got a big sample size. We've got 120 adults now from Greenton, so we don't want to be working with a binomial distribution to figure out the probability that more than 75 own a car. And that's why we're told to use an approximation. So if you're doing this in A level, you've got a whole bunch of approximations that you need to think about. But in AS, the one we're looking for here is the normal approximation to the binomial distribution. So to do a normal distribution problem, we've got to have the mean and we've got to have the variance and the standard deviation. The mean, mu, will be NP, which is 0.7 times 120, which gives us 84. And the standard deviation is NPQ, which is 84 times 0.3 from up here, which gives me, what did I figure out, 25.2. Okay, this distribution up here is what I'm going to call X, right? So X is binomial with N and P. Our approximation, I'm going to call X dash, is approximately normal with mu of 84 and sigma squared of 25.2. I have to use a continuity correction though, and the reason for that is that this distribution is a discrete distribution. So the probability that X is greater than 75 is the sum of a whole lot of bars in a bar chart. And I don't want the 75th person there. I want 76 and 77. So I'm going to colour this one in, and it's going to show me where to do my continuity correction. Because what I'm doing here is I'm sitting my normal approximation over the top of that bar graph. So I've got probability that X dash is greater than 75.5, right? Because I just want this bar here. So that equals probability that Z is greater than 75.5 minus 84 divided by the square root of 25.2, right? So I'm standardizing and I'm asking how many standard deviations below the mean is 75.5. When I chuck that into my calculator, we're going to get the probability that Z is greater than negative 1.693. Let's draw a picture. Here's my picture here. So I want that area there, but that is equivalent, because I'm using the tables, of this thing here, which is phi of 1.693. Right, so phi of 1.693 I have to get from my normal table, which hopefully is on the next page. Right, so I'm going through here. I've got 1.69, but I have to do 1.693, so I've got to add on those little 3 points to 0.9545. So that's going to give me 0.9548. And I need to round that to 3 sig figs, and I get 0.955 to 3 ESF. Now I'm running out of time to do question 6, plus I have to go out for dinner. So I'm just going to introduce it here, and I will video it later on, probably later on tonight, maybe tomorrow morning. Question 6 is a probability tree one, and it's about red and blue balls, and we have to take one and put it into the next box. So box A has got 8 balls in it, 7 red and 1 blue, and then box B starts off with 9 red and 5 blue, and then it gets an extra one put in from box A. So what we've got to be careful of is how many of each colour are in at each stage. We've got to label up our diagram and then solve some pretty simple questions, but I will do a proper video on that later on. Thanks for watching.